All right, so welcome everyone to Can We Have Compliant Carbon Negative Cement? This course is brought to you by the GreenHome Institute. The GreenHome Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I'll be your moderator. My name is Brett Little. I am the program manager here. As always, our courses are approved for multiple continuing education units. In this case, I've got too many logos there, but it is approved for our materials pedal in our certified green home professional, as well as AIA, health, welfare, and safety, which may make it applicable to your state-based design or contractor license. A big shout out to some of our member news announcements. Apparently Green Build is doing Green Build at Home, which is pretty cool. And I'm dropping a link in there, but our member, Tom Bassett Daly, Architects, is going to be presenting as a portion of that session on home renovation and electrification insights. So make sure to check that out if you want to see Tom in action. And you know, our members are doing amazing things like this. So sign up to become a member, get access to our free webinars, get this mug. We've got a few of these corn-based USA made mugs left, and all sorts of other benefits. And before we get started, a huge thanks to all of our sponsors who allow us to do what we do, especially today's sponsor, the Rheem with the brand new 120 volt instant plug-in Proterra model. So this is a heat pump water heater, whereas in the past, they had to require, especially on existing housing and low-income housing especially, they had to require special electrification and expensive improvements. These typically can just be plugged right in with less cost and hassle. Rheem is an Energy Star Award 2022 Partner of the Year for their efficiency of their heat pump water heater. Up to 400% efficiency. The way these things work is they suck in heat from the top. As you can see, it goes down through a filter. It gets absorbed through a refrigerant, compressor, and the condenser heats the water tank, and then there's a condensate line from there. Again, super energy efficiency, especially compared to standard electric or even gas systems. They've got warranties on it. They've got leak detection. Lots of things you can do with your smartphone to control this device if you want to set it up for that. And they can be strung together in a multifamily setting. They can be ducted or be ductless if you want them to. And they're starting to work great with time of use programs. These water heaters actually work like batteries. So they heat up water when costs are low, carbon is low on the grid, and then they may keep that water stored during the peak load, high energy use times. So go check out both the Rheem Prestige and the new 120 volt Proterra there at rheem.com. And then also talking about embodied carbon, help reduce embodied carbon in your projects by selecting rock wool. We've got a mineral wool application that uses less carbon compared to foam. And they have a pretty cool R-Class builder event that you can sign up with. They've got one coming up on August 4th, and they're going to be talking about a project they have going in Arizona in a WUFI zone between Rockwool North America Comfort Board and LP Flame Block MGO board, a building that's really built to design and suppress or prevent wildfire resilience, something we all need a little bit more of. So you can check them out at the R-Class on Rockwool. And before we get started, I'm excited to be adding this session among many of our other sessions on our growing list of embodied carbon channel. You can check that out on our website as well. And so that is just a growing list of places where, again, you can learn about this important topic. We talked a lot about operational energy, net zero all the time. Now we need to talk about embodied carbon. We've got Chris Magwood with the Beam tool coming on August 17th. Very excited. If you're doing our Green Star program, you know, if you're doing a new construction certification, you do have to evaluate and reduce your embodied carbon, especially at higher levels of Green Star. So that is a requirement now within our green building program. So with that, I am super excited to have Cody here today, who is not that person in that photo, but who is the real person on camera. Apologies again, Cody. And Cody, I'll let you talk about yourself and your company and what you're up to. And just please take it away. And thank you for joining us.
Yeah, thanks, Brett. And thanks again for the opportunity to talk today. I'll give a brief personal background and then start sharing my screen. So, my name is Cody Finke. I, because my quick academic background, I'm a chemist by training. I got an undergraduate degree in chemistry, and then I got a PhD in environmental science and engineering, and have been working on ways to make industrial processes lower impact on the environment for about I guess last 9 years throughout my PhD, uh, and then throughout founding this company Brimstone. I founded or co-founded Brimstone about 3 years ago now, and we have the mission to decarbonize the cement industry globally. And we'll talk about a bit about why that's an important and interesting problem and what our strategy is during the presentation today. So background of the company, we're fairly early stage. We have we're making kilograms or so of product at the laboratory scale, and we are doing in the basic engineering phase on building our first demonstration scale manufacturing plant, which will make hundreds of tons of product per year. And hopefully, if we're successful, it will demonstrate that this process can scale to the relevant scales required for a global industry. And yeah, so the company, I guess in startup jargon, we're a Series A company. We've received investment of around in total just over $60 million from several fairly well-known groups, including Breakthrough Energy Ventures, which is Bill Gates and all of his richest friends who are concerned about decarbonizing decarbonizing the world, and then Amazon Climate Pledge, which Amazon's fund focusing on decarbonizing. Fifth Wall, which is a notable real estate development fund. DCBC, a major venture capital fund in the Bay Area. So several of these sort of major groups. And that's probably good enough background about me and the company. So from here, I'm going to jump right into the presentation. So I will check with Brett before this, but Brett, can you just confirm that you can see the presentation or somebody?
Yep, perfect. Yep.
Great. Thank you so much. So as I mentioned, the goal is to decarbonize cement and ultimately, therefore concrete. I'm going to start with a little background on cement and embodied carbon, and then I'm going to go into get a little bit more interactive. So here's just some interesting facts about cement. So cement, of course, is the binder in concrete. That's the stuff that sticks everything together. The production of cement is responsible for about 5.5% of greenhouse gas emissions. That's also commonly said 7.5 or 8% of CO2 emissions. Both those numbers are true. CO2 emissions only account for about 70% of greenhouse gas emissions. So that's why greenhouse gas emissions are that's what the real problem is. That's what I like to say. This number is about the same as cars. Cars are, the world's cars are responsible for about 6.5% of greenhouse gas emissions. So cement is a pretty sizable category. It's among the biggest single categories. And one of the things that I and we at Brimstone like about it working on this problem is it's not so commonly worked on. So we have an outsized chance of being impactful in the climate space. So a few other interesting things. So concrete, which is of course the building material, is responsible for, it's the most consumed human-made material on the planet by mass. The only material that's consumed more is water, which is hard to argue is human made. It's, the cement and concrete industry represent about $1 trillion market, and it's broken down by, by those bars in the lower right. It's projected to grow. It's one of those things that's, necessary for, for development as we know it, and it therefore, tends to grow with GDP and population. So, as countries in the world continue to develop, and I hope that they do, so the quality of life for people all over the world increases, then it's expected, and so far has been the case, that the consumption of cement and concrete will also increase. Now, this would, of course, lead to massive CO2 increases if we use the same process that we use today. Hopefully, Brimstone could stop that. Okay, so now I'm going to chat about how cement is made today via the conventional process. So today, cement is made from a rock called limestone. Limestone has the chemical formula calcium carbonate. That's where my mouse is here. And how you make cement is you take limestone, you mix it with a source of silica and alumina and iron oxides, which is typically clay, but can be others. Grind it into a powder and put it into a kiln, and typically with a pre-calciner. And in that kiln, you first get a heating step up to 900 degrees Celsius. And at that step, this reaction in red occurs, where the limestone decomposes into lime, which is calcium oxide, and CO2. So this chemical reaction here is why cement is considered difficult to decarbonize. And that's because these CO2 emissions have nothing to do with a fossil fuel. They have to do with the chemistry of making the product. So the CO2 is embedded in the rock, and when you heat that rock up, you release the CO2 into the atmosphere in order to make calcium oxide. So another way to say that is, if we were to use 100% clean energy with the conventional way to make Portland cement, about 60% of the CO2 emissions would persist. So then the other 40% of CO2 emissions from making cement comes from this heating. So you have to heat to 900 degrees C, which is actually where the major energy consumption is. And then you heat again to 1450 degrees C, or further to 1450 degrees C, in order to make the final Portland cement product. And that's cheapest done by burning a fossil fuel. And so that's what's done today. Okay, so these two images, they represent a cement plant. There's also more that goes into it. So typically you will also add in something called supplementary cementitious materials. Many of you involved in construction may know these by that name, or by fly ash or slag. These are, or pozzolan. These are materials that are mixed with the cement to enhance properties some way. So big thing they do is they do something called mitigating the alkali silica reaction, which can prevent cracking. And other weaknesses. Other things they do is they can enhance density properties, or in many cases strength properties, which can be useful for modern buildings. These so the interesting part about fly ash and slag is they also are related to the carbon economy. So fly ash and slag are both waste products of burning coal. So fly ash comes as a waste product of burning coal in a coal-fired electricity or coal-fired power plant, and slag comes from burning coal to make steel. Both of these products are diminishing because coal is no longer the cheapest way to make electricity, and coal is also no longer the cheapest way to make steel. It's cheaper to make steel by recycling steel scrap via the electric arc furnace, and it's cheaper to make electricity either by natural gas or renewables. And those processes don't produce any or produce very little of these fly ash and slag components. So they're becoming scarce and therefore much more expensive. And then this final product, this mixture of supplementary cementitious materials and Portland cement, is what we call cement. And that is the binder and goes into being mixed with sand, gravel, and water to make concrete the building material. So what we say at Brimstone is the conventional cement process is sort of two problems. One is a problem for society, which is it's very CO2 intensive, and more importantly, it's not just an energy problem. So we can't think about it in the same ways that we've thought about other CO2 problems, like energy that's used in a building, for example, is it's mostly operational energy. That's all energy and fossil fuels. You can't think about cement in that way because most of the CO2 emissions have nothing to do with a fossil fuel. And probably problem two is that this essential component of making modern cement is becoming scarce, and that's a problem for the industry, not just society. Okay, so with that background, I'm gonna pose this question to everyone here, which is, what needs to be true to decarbonize cement? So I've never asked this before of an audience, but I'm curious, what folks think would need to, from perspective, everyone in this audience is, related to construction at some scale in some way. And I'm curious what people think needs to be true in order to decarbonize cement, as in, what would be necessary on a global scale, not just like for you personally, in order to decarbonize this industry. So please, I don't know if people can unmute themselves and answer, or if you throw things in the chat. Love to hear people's thoughts.
Yeah, no. As far as unmuting, that would be difficult right now. But I would encourage everyone to drop into the Q&A just some general thoughts that you have, and maybe if you're thinking about it as we're going through the session, maybe we can get to some of them too at the end, right? And go through them. And then also for those of you listening to this on demand, put it down in the comments, get engaged on the session. We do want to hear from you too, even though you're not here live with us today. So please drop it in. So we're seeing some stuff come in here. We're looking at carbon capture, OD, CO2 product and calcination, building codes and other incentives to build with low embodied carbon. That's an interesting one.
Yeah, and I'm also seeing a lot of good things in the Q&A too.
Yeah. So I don't know. So if you can see those, go ahead and take it. So
yeah, okay. So I see a lot of really great answers. So I'd love, had one answer saying, or several answers talking about finding an alternative to Portland cement. So several people saying on an alternative. People are talking about geopolymers, which some people know about. Someone mentioned hempstone. This is, so I think that those are all great solutions. So basically, this is the solution that says finding a new material. So can anyone think about what are the challenges with new materials? Like why like that? It's, certainly you could imagine a new material that could be zero carbon, which could be great. What could the challenges be to scaling that globally?
And I really, I like the code question in there because, first of all, it's part of the title of this event, right? But I would be curious if you plan to kind of get to that, like, can the codes either pave the way for this or get out of the way of this? Are they in the way? And so I'm curious if that's something you'll be talking about.
Yeah, Brett, I absolutely will. And I think I'm gonna jump in there directly after this.
Okay.
Essentially a lot of these, what folks are saying is, a new material that's not currently regulated. So geopolymers, for example. So that's, you're kind of pointing to one thing. And Brett, I think that was a great answer to the question. So one of the challenges is, and I'm sure if there's any structural engineers in the audience, y'all can chime in here, is if you use a new material, and you have to trust that the building you built with that new material is not going to fall down. So that is a fairly easy thing to do in theory, but it's very difficult in practice. I'll give you an example. So if you are a structural engineer, or if you know one, then they are often in the unenviable position of certifying or specifying building materials for a building. And let's say that building is a mid-rise building in, I don't know, downtown Lincoln, Nebraska. And if that building were to fall down, then, potentially hundreds of human lives could be lost. And also, hundreds of millions of dollars could be lost. And that's something that I think we could all agree no one on this call wants. So cement is about 1% of the cost of building a building. Concrete's a little bit higher, but the cement fraction of the concrete's about 1% of the cost of building a building. So even if a new material is cheaper, there's not that much financial gain by replacing it. So the only gain is a CO2 emissions gain, which is a great moral gain, but there's also the moral hazard of this being a new material that no one's ever built a mid-rise building before, let alone a mid-rise building specifically in downtown Lincoln, Nebraska. So it becomes a pretty risky proposition to try to use a new material, knowing that we already don't fully understand this material that we've been using for 100 years, Portland cement. So using a new material that we also don't fully understand, or even understand even less, just becomes a lot more risky. So what tends to happen is people are slow to adopt new materials, and that can be a problem. So while new materials are, so that's one of the challenges. But like we said, it could be a great solution, because new materials could also be zero carbon. So besides new materials, I'm just sort of scrolling through the chat here. So someone said affordable and easily accessible for mainstream adoption. So I think that's a really good point too. So we're talking about globally. We're not talking about for just wealthy people. So I think this is like a really important point, that we need this to be able to be used by everyone in the world. And Portland cement is quite affordable already. And then the other thing, so we need something to be similarly affordable to Portland cement. And I would even argue that it has to be lower cost than Portland cement, because again, in the absence of massive structural change in the world, I don't know of any material or of any process that has gone from lower cost to higher cost. Things tend to, new products tend to replace old products because they add more value, and are therefore lower cost. You can think of it either way: adding more value or lower cost. So so affordable, I think, is a really good thing for global adoption. So reduced energy process. So that's, energy, like we said, energy is 40% of CO2 emissions for cement. Like that would be reducing energy is a surefire way to reduce CO2, or near surefire way to reduce CO2 emissions. That could be important. It doesn't solve the whole problem of cement. It solves a minority of it, but it could be an important one. So anyway, these are all great answers. So I'm now going to talk about what we think needs to be true and how we think about it. So we have three basic things that need to be that we believe need to be true. So we think that in order to decarbonize cement, you need to make the same material that's made today. We need to make a lower cost material. And then the most basic thing, it needs to be zero carbon at least, right? So the third one's fairly obvious. If you're going to decarbonize cement, it's got to be zero carbon. That's kind of circular reasoning, but I think it's important to state. The second one someone else mentioned, so lower cost, and we'll talk about how we think about that. And the first one is, I think, maybe somewhat controversial in this group: same material. So I'm going to start with the same material question. I thought that was going to be the most controversial. So when we think about the same material, I don't mean that it's strictly necessary for it to be the same material in order to work as a building material. I think, that would be a ridiculous assertion. Of course, alternative materials can be used, and I think they should be used. I'm a big fan of geopolymers and biocements and other types of cements. But I'm concerned about the speed of adoption. So I'm going to start with saying, what's necessary for speed of adoption. So this is a graph from the most recent IAPCC report. I pulled this from the data section, which at the time I pulled it was still subject to revision, but I think it's final now, so I'll probably take that off. And what this shows is it shows global warming temperatures on the y-axis, and then time as measured in current years or future years on the x-axis. So right now at this break here is present day. We're in 2022, and we've got several scenarios which are called shared socioeconomic pathways. And these are basically saying, okay, there could be radical technology development, or we could do nothing, and all these sorts of things. And you can see the most hopeful scenarios where Earth warms about 2 degrees C, about 2.5 degrees C, and about 4.5 degrees C. That's light blue, dark blue, and orange here. All require a net zero CO2 emissions in 20 years, 60 years, and 80 years respectively. So the world needs to be producing net zero CO2 emissions. Okay, so 20 to 80 years, those years, that sounds like a long time. But I'm here to tell you that it's not actually a long time. So, I think when we think about that, actually, we'll just go to the next slide. Okay, 20 years. Why is that such an urgent timeline? So if we look at history with energy transitions, to go from 5% energy production to 25% energy production, in general, it takes about 50 years. So that was true with coal, that was true with oil, that was true with natural gas, and no other new energy has yet reached 5%, yet reached 25%. So we can't tell how long it has taken to go from 5% to 25%. And in fact, no energy except for nuclear has reached 5%. Besides these fossil fuels. So when we look at, wind and solar electricity, which are here represented by white, they sort of came on the market sometime in the, started being a reasonable or measurable fraction of global final energy in, the 1990s. And it is now, early 2020s, and they still haven't reached that benchmark. This graph happens to only go to 2015. I have another graph in the supplemental slide that shows the more modern data. So it's been 30 years or so already, and we're still not at a major transition to renewable. So we're not, it takes some time. So if we talk about we have 20 to 80 more years, we really have to work as fast as possible. So this is also true in the cement industry. So in recent history, there have been 2 major processes to make cement. One's called the dry process, and one's called the wet process. The dry process was invented in the 1930s, and in 2006. The dry process was only responsible for about 75% of global cement production, and is 25% cheaper. So even with economic tailwinds, it has taken over 80 years to transition fully from the dry process to the wet process. And I should have explained this graph. So this y-axis is million tons of clinker, that's cement produced in cement plants, and then Black, red, and blue are all dry process. And then green, yellow, and purple are all wet process. So as you can see that basically new plants have all been dry process, but the wet process plants have been very slow to shut down.
I just want to make sure I heard it correctly. The more sustainable approach is the dry. The cheaper approach is the dry process, right? For some reason, I thought I heard it the other way for a second. So
no, sorry. Yeah. It's the dry process is lower energy. So it's both more sustainable in terms of CO2 emissions and lower cost.
Does that also include, is there I personally am in a drought, other areas are in a drought. Is this a water intense process? So just to me, I hear it goes from wet to dry. Maybe there's less water involved.
Yeah, there is less water involved. Water's not it's not a huge consumption point in cement in general, whether it's wet or dry, but certainly there's, much less water involved in making dry process cement than wet process cement.
Great. Thanks.
Yeah. Okay. So this is a graph that shows, converting, ways to make steel. So on the y-axis, you've got percentage of total steel produced via the different processes, and then years on the x-axis. And as you can see, again, it takes 50 or 100 years for an old, less efficient process to completely go away. Like if you look at the Bessemer process, right, as I mentioned in 1860, it didn't fully go away until 1980. So the timescales for global transitions historically have been very, very long. And that's been true in modern transitions too. So when we think of adding an additional thing like convincing people to use a new product, what we hear is that will take longer because there's this risk that I already mentioned associated with building new buildings out of materials that we don't fully understand. And I want to be very clear again, I think that these materials are great. And I think that that we have the ability to fully understand them, but there is an additional requirement of time that is concerning. So that's one of the challenges with new materials. Okay, so I think I'd love for folks to put comments on the same material piece in the chat, so maybe we can address those at the end of this section. Okay, so the next thing is lower cost. So someone mentioned affordable cost, lower cost, so synonyms. That's something that we believe needs to be true. Again, I don't know of any process in history that's gone from lower cost to higher cost at a global scale. I think there are places where higher cost is tolerable, especially in high income countries. But again, we all share one atmosphere. We need to decarbonize cement globally. So higher cost tends not to be tolerable at a global scale. And like when I think of that, I think about carbon taxes. So, the thing about carbon taxes is carbon taxes are used in order to try to make higher cost processes that are better for the environment lower cost. Or another way to say it is, try to internalize externalities, right? Right now, we don't directly pay for the effects of increased CO2 emissions. And we say, let's internalize those costs of CO2 emissions. So yes, I think I think in general, those are good things, and that, carbon taxes and trying to internalize the externality of CO2 emissions is a good thing. But I think that it's also very slow. So when I think of my home state of Washington, so forget, maybe 5 years ago now, it was 10 years ago, we voted on a $15 per ton CO2 tax. And that $15 a ton CO2 tax, even in Washington, which is among the most environmentally friendly states, our governor at the time, Jay Inslee, recently ran for president on a climate agenda. Washingtonians, we love our glaciers. We're very concerned about climate. That $15 a ton CO2 tax did not pass in Washington State. So getting higher cost processes that are better for the environment, I think, again, will be very slow. And we don't have slow. We have 20 to 80 years. So I don't think that it's reasonable to expect that a higher cost process will be fast enough. So with that, I'm going to talk about briefly talk about electrification, because electrification, I know, is probably near and dear to the hearts of many people in this room, including myself. Especially when we talk about trying to reduce CO2 emissions, operational CO2 emissions in buildings. For example, my landlord just installed a heat pump, which has been great for me. We have an electric water heater. These are all great, and we have electric stove. These are all great things that work really well. However, there's challenges with electrification in heavy industry, and those have to do with cost. So this graph is dollars per gigajoule. That's a unit of energy. And this bar graph shows various types of energy. So from the left, it's solar energy plus storage. That would be like 24-hour a day solar energy. There's also coal electricity, geothermal electricity, combined cycle natural gas electricity, utility scale solar, which does not have storage, so it only produces energy when the sun's out. Utility wind, same, only produces energy when the wind's blowing. Natural gas heat, so that's just burning natural gas for thermal energy. And then coal heat, just burning coal for thermal energy. So as you can see, burning a fossil fuel to make heat for energy is by far the cheapest source of energy. And it's much cheaper than 1 cent per kilowatt hour, which there are a few wind and solar projects around the world that meet that 1 cent per kilowatt hour about 20 to 40% of the day. So when you so let me just double down on that. So in a home, electricity can often be the cheapest, not only the better solution for the environment, but also the cheapest solution. And that's because it's much easier and more economically efficient to move electrons long distances through wires than it is to move a physical thing like coal and natural gas. You have to build pipes, or you have to deliver coal in a truck. Transportation is very expensive, whereas for electricity, you just have to build a wire, and then after you build the wire, transportation is nearly free. Whereas if you're doing something in a big centralized way, which usually decreases the cost of the big centralized thing the most, then that transportation is much easier because everything's going to one place. And you also have huge economies of scale. It's not like the small amount of energy you're consuming at a home. It's an enormous amount of energy that you're consuming in one place. So these burning fossil fuels for thermal energy are the cheapest form of energy. So that's one of the other problems that makes cement difficult to be zero carbon, is that currently cement is it uses heat from a fossil fuel to power its process. And if we were going to electrify that process, which is 100% possible with today's energy prices, that would increase the cost substantially. And the cost of utility solar and wind or other renewables would have to come down a lot in order to be competitive with the cost of natural gas or coal, which is really the cheapest. So another problem with cost and decarbonization is the intermittency problem. So as you can see, the cheapest form of energy comes from utility solar or utility wind, which is intermittent. It's only around when the sun is shining or the wind is blowing. So wind currently on average in the US blows about 40% of the time at a way that you can produce energy. So if we were to power a cement plant, so that has implications for the capital cost or the amount the cement costs to build. So here on the y-axis again is the cost contribution per ton of cement, and then here is various capex and opex. Okay, so here's what we say: cement capex maybe is $35 per ton, and cement opex is $30 per ton. So this is like energy consumption, everything else is opex, and capex is building the plant. So the total production cost of cement is about $65 per ton. The energy opex alone of cement is about $15 per ton. So that's buying typically coal in order to fuel the cement plant. If we were to use wind energy instead of coal, then the OPEX would go from $15 to $24. This is wind-powered cement OPEX over here. So we would increase the cost of energy, so that increased the cost. But the much more concerning thing is actually the CapEx. So in order to in order to produce the same amount of cement in the same amount of time, right, we would need to build a plant that is 2.5 times bigger than a conventional cement plant, because that plant would only operate 40% of the time, because that's when the wind is blowing. So that would make the CapEx, 2.5 times higher, leading to an $85 per ton CapEx for that wind-powered cement plant. And the CapEx alone would be higher cost than the total cost of producing cement today. So these are the challenges associated with, using electricity or renewable electricity to make cement. It's not that it's not possible, it's totally possible. It's that it makes a higher cost product today. Hopefully that's not true in the future, but that's the problem today. So, with that 20 to 80 year timeline, what we say is like, well, we can't really wait for the future. We have to have a solution that works today. And, electrification with technology today doesn't really seem like it works because of this cost issue. And again, if you want a global solution, it's got to be lower cost.
Cody, real quick, some two questions here on the energy choices you have on your chart, the former chart anyway.
Yeah.
And we don't have time. This could be like hours and hours of debate on its own. But the question, of course, is where is nuclear on your chart? And then there's another question about where is solar storage. So I don't know if you can briefly address that, especially the nuclear. Oh, it is there. Okay, somebody, I don't know what they were talking. Okay, anyway, so just the nuclear one.
Yeah.
I think they were talking about not solar battery storage, but hot water, like the concentration plants. So could you address that and then just briefly speak to nuclear? Because I know, again, that could be a lot of conversation that we can't get into now. So
yeah, absolutely. So nuclear is typically about about the same price as coal. Sometimes it's a bit lower, sometimes it's a bit higher. I think that there's a lot of with all of these, there's emerging technologies that could bring the cost down, which is great. Solar plus storage. So there's lots of ways to store energy. I've been non-specific here. It turns out that I'm just using the lowest cost one, which today with modern technology is batteries. There's also there are solar thermal plants that can store heat and then turn that heat into electricity, and they tend to be a little bit higher cost, except in rare cases like I think Ivanpah, which is over in the Nevada desert near Las Vegas, because it's such a sunny hot place. You can have some cheaper. But what I would do is I would direct people to what's called, if you I don't know if people can see the chat, but if you look at the Lazard levelized cost of energy, you can go answer all of these questions for yourself. So Lazard is an enormous global financial services firm, and I like them because they don't have a horse in the game. But the Department of Energy also puts out a pretty good one. You can also look; it's tends to be about the same as Lazard's, and Lazard and they calculate the levelized cost of energy for lots of different electricity projects. And you can see nuclear, solar plus different storage, utility scale solar versus residential solar. And you'll see residential solar is quite a bit more expensive than utility solar, and it's economies of scale. So those are sort of all the all these things here. But yeah, so I couldn't. There's about 1,000 more ways to make energy. I just put sort of the popular ones here. So if your favorite one, like hydro, is not here, that's quite cheap. Also, it tends to be 3 or 4 cents per kilowatt hour. So anyway, there's lots of other ways to make energy, and I would direct you to Lazard levelized cost of energy for all those things. And then I will say one more thing. So it's a hard problem to make electricity of any kind, whether that's nuclear or fission, nuclear fusion, geothermal, coal, natural gas, any type of electricity, it's a hard problem to make it cheaper than heat. And that really comes to a fundamental thermodynamic reason, which is that electricity is ordered energy, or it's really pure work. And I mean the physical definition of work. Whereas thermal energy is disordered energy. So if you want to turn disordered energy, or if you want to make ordered energy, you always have to pay an entropy tax. So entropy is, the fundamental thermodynamic property that describes order, and it's generally true, or it is true that entropy always increases, or in theory it could be zero, but it really always increases. So if you're trying to fight entropy in a localized system to make electricity, then entropy has to increase somewhere else in order to do so. And that's what we think of in thermodynamics as like the entropy tax. And in order to make electricity, you have to pay that entropy tax. So it's hard to imagine that a type of energy where you have to pay that entropy tax will be substantially cheaper than a type of energy where you don't. So that's one of the fundamental challenges with making electrified energy cheaper than thermal energy. Okay, so the last piece of what we believe at Brimstone needs to be true in order to be zero carbon is that you have to make a zero carbon product, right? So it's sort of, again, it's very circular logic here, but also it's the only thing that is true. But why it's important is because we believe it has to be zero carbon under the context of point 1 and point 2, right? So what we really think is that the least cost way to operate the piece of the machine has to be zero carbon, or else it's not going to be a zero carbon solution. Because let's say that some maybe bad actor somehow steals Brimstone's intellectual property and starts building cement plants with it because it's a much cheaper way to make cement, and they are solely financially motivated, and they decide to build cement plants using their cheapest form of energy, which happens to be coal, and therefore, and in that case, we want to be really sure that our product is substantially lower emissions than the conventional process, even under the context of that scenario happening. And I bring that up is because it's actually a pretty common scenario in the global economic system, right? So it's fairly common that like whether it's through stealing or patents running out or clever litigation, is that other companies will start doing what you're doing. And in that case, you can't control whether or not they use coal or solar energy or whatever. And probably like most folks who are interested in stealing intellectual property don't do it because they don't want to make the most money, right? They do it because they want to make the most money, and therefore they will use the cheapest source of energy. So we think that it is essential for any technology that meets the first two criteria to also be a zero carbon technology. So I'm now going to talk about, I'm going to talk about what we do now, but I'm going to pause for a second and look at the Q&A just to see, please put some stuff in the Q&A or chat if you have any questions about like the first 2 points that I was making.
There was an interesting question about the wet plants being converted over to dry process. Is that possible? Is there a payback?
Yeah, it's super possible. So basically the difference between the wet process and dry process is fairly simple. In the wet process, you add water into the milling and grinding, which helps lubricate the milling component, and you end up with a wet slurry of limestone. And then you put that into a kiln, and that you have to use extra energy to evaporate off all the water in the wet process. Whereas in the dry process, they've invented a new milling technology that doesn't require water lubrication. And when I say new, like this was new in 1930, right? It's not that new anymore. And it's lower energy and lower water because you just don't need the water as the lubricant. So it's about 25% lower cost, and all you need to do to convert is to replace the old mills with the new mills. And then you can also, there's also lots of other efficiencies you can add by replacing the kiln and all these kinds of things. But in general, it's a very doable retrofit. It's often not done for lots of reasons. So one reason is that the old plants are a fully depreciated asset, which means that the capital cost is fully paid off and they're just printing money at this point. So the payback period is maybe longer than the lifetime of the other equipment. So it's not worth it to do this retrofit from a financial perspective. Other reasons is they might be in a regime where the cement plant is burning garbage, and maybe the city pays the cement plant to burn garbage. So using more energy might be financially beneficial. So yeah, this is a big problem. Retiring old plants. Building new plants that are cheaper is a no-brainer, right? All of the new plants that are built today are dry process plants. No one built a wet process plant anymore. But retiring old wet process plants takes a long time because there's that financial challenge.
In the calculations you have there on the energy costs, was transportation part of that factored in? Is that a large amount, a very small amount?
That's a great question. So transportation is a tiny, tiny amount. In there's transportation internally, so from the quarry to the cement plant was factored in, but from the plant gate to the concrete plant, it was not factored in. But I recently saw, so I was recently part of a panel where they actually presented numbers. So 89% of energy consumption happens before the plant gate. So like in concrete, so transportation, making the concrete, pumping concrete up into the building site, all of that stuff is 11% of energy consumption, and transportation is a fraction of that. So it's a pretty small component comparatively. And then of course energy consumption is only 40% of CO2 emissions. So you can see how the math ends up.
Thanks.
Yeah. Okay, I'm just scrolling through here. Any questions or comments about the low cost or same material piece? Please don't be shy. Looks like not seeing too much else. Awesome. Okay, please, if you have any comments, and this is a great place for disagreement about same material, lower cost. Please, I'd love for this to be a discussion. Okay, so zero carbon, right? That's what we're here for, right? I got a PhD in environmental science and engineering. I didn't do that to not be zero carbon. I didn't do that to work on technology that's not zero carbon. This is what. So how do we do that? We talked about how Portland cement, how CO2 emissions mostly come from the rock. So we said it has to be the same material, and you can't use CO2. You can't use limestone because that has CO2 in the rock. So you have to use a different source of rock, right? So you have to use a source that has calcium in it, just like limestone does, but does not have CO2. It turns out that there's a rock that is about 200 times more abundant than limestone, called a calcium silicate rock. So this is, for example, a basalt. But there are many, many, many other examples besides basalt. They're about 50% of the Earth's crust, and they have calcium in them, but they do not have CO2 in them. We invented a chemical process which extracts the calcium from these rocks and turns it into Portland cement. And thereby it totally eliminates the process CO2 emissions. So there's no CO2 in the rock. So there's just no CO2 that's produced from the rock. The other clever thing that it does is it takes the silicate fraction, it turns that into a supplementary cementitious material. In our case, our favorite supplementary cementitious material is class F fly ash. That's a conventional material that's made today. We can make an SCM that passes the ASTM standard for class F fly ash, but we can also make others. But what that means is from a single plant, you can make both Portland cement and SCM. and therefore make the exact same cement that's used today, no difference whatsoever. And then you can make the exact same concrete and building material that's used today, no difference whatsoever. So if a cement company were to use our process instead of the dry process, which they use today, then they could vertically integrate their production of SCM, which could be of huge financial benefit to them. So in this way, our process could be lower cost, and it can also be the same material, and then it can also have zero process emissions. Okay, so there's still energy emissions, right? And we hope that we can use clean energy, and we hope that clean energy technologies can meet that lower cost threshold. But we also want to plan for the worst case scenario for more carbon intensive technologies that are currently the lowest cost energy source. So our process, it turns out, or I should say, all of these rocks, it turns out, also contain this element magnesium. And it comes out of our process typically as magnesium hydroxide. And magnesium hydroxide just sitting in air will passively, permanently sequester and mineralize CO2 from the air. So we make this waste, our process makes this waste product, magnesium hydroxide. It reacts with the air to form magnesium carbonate, which is the magnesium version of limestone, and that will sit around for over 5 billion years and not do anything. So this is as close as it gets to permanently sequestered CO2. So it turns out that even for a conventional fuel mix, this magnesium waste product leads to a carbon negative cement. So that's what this graph shows here. So here's kilograms of CO2 per ton of cement on the y-axis. Here is, pure coal, which almost no cement plant uses. On the on the x-axis you have conventional cement versus brimstone cement. So here's pure coal, which almost nobody uses. Here's in the middle line is either natural gas, or it's a mixture of coal plus refuse derived fuel or engineered municipal solid waste. And then, so that'd be things like tires or, solid waste pellets or things like that. And then the bottom dashed line is clean energy. So as you can see, the conventional process would be about 500 kilograms of CO2 per ton with clean energy, about 700 via the conventional way to make cement, and about 900 if you used pure coal. In our process, it's quite different. So with clean energy, we would be about minus 500 kilograms of CO2 per ton. With a conventional mix, so a coal plus refuse derived fuel would be about minus 100 kilograms of CO2, so that's carbon negative. And then if we were to use pure coal, would be a little bit carbon positive. So that's our CO2 emissions mix. But you don't actually have to believe me. So for the first time I'm sharing, we just, back a little bit earlier this month, we had a third party do a life cycle emission, an LCA, life cycle emissions analysis on our process, following the ISO standard and the same standard that's used for environmental product declarations. And they found that our global warming potential was minus 131 kilograms of CO2 per ton of Portland cement, using a conventional mix of coal and refuse derived fuel. I'm going to compare that to the environmental product declaration, an environmental product declaration that I just pulled from the LC3 tool, which some of you might be familiar with, which shows a very good cement here. So this is Lehigh's EcoCem, which is a very low emission cement, which is 679 kilograms of CO2 per ton of Portland cement, so quite a bit higher, as you can see. So anyway, this was great news for us that a third party validated our result. It's also, I think, great news. It's a great milestone for the company. We're excited to, we're definitely excited to move forward with this process. So that's all I have. I guess we're about at time. I will mention, so this is our last slide. So I would love to hear from you if you're a chemical engineer and you're curious about working at Brimstone. I'd love to hear from you if you're connected in some way to greater than 10,000 tons of cement production or greater than 40,000 yards of concrete purchasing. 10,000 tons of cement purchasing or concrete or greater than 40,000 yards of concrete purchasing. And I'd also love to hear from you if you're a policymaker, and that could be public policy like laws, or it could be standards like LEED, ASTM, or ACI. If you're involved in making those, very interested in chatting with you. So please send an email to info@brimstone.energy, and that will get to me. So yeah, thank you so much, and happy to take any questions or comments or free-floating anxieties.
Yeah, thanks so much, Cody. And before we get to some of those questions that came in, just a reminder, this session is being recorded. You can subscribe to our YouTube channel and get access to it, share it, rewatch it later at your leisure if you want. And just another reminder here, well, things are moving very slow. If you're looking to get your continuing ed watching this on demand, not right now, take that quiz with an 80% passing rate on whatever channel you're watching this on, Thinkific, USGBC, and you'll receive your certificate. If you're watching this live and you've been here for a majority of the session, you can check your spam at certs@gutenbergcerts.com and get it that way. And as those questions are coming in, again, just a huge thanks to our board of directors, our executive director, Jose Reina, our nearly almost 250 members, and all of our top tier sponsors who allow us to keep doing these sessions. Mitsubishi, Rheem, April Air, and thanks to all of our other sponsors who allow us to do what we do. So Cody, there was a question that came in about basalt and just some more specific details about the availability of it worldwide.
Yeah, great. So basalt is one example of a rock we can use. We can use many other rocks. So I'm going to talk about the specific class of rocks we can use called calcium silicate rocks. And those are about 200 times more available than limestone, which are the rocks that are used today for cement. So there's the scarcity of rock is not an issue for us. We have other issues, but that's not one of them.
Yeah. Oh, okay. Great. So yeah,
I also see a question from Brian about type 1L cement.
Yeah. So I thought they were saying a type of cement in Illinois. So you know what he's saying.
Yeah.
So
that's what that is that's Portland cement type 1, but it has mixed limestone in it. So they mix, I think it's up to 15% limestone.
Mm-hmm.
So you can actually see, if you zoom in on this EPD here, that this EcoSem is a type 1L cement. So basically how they reduce cement, how type 1L cement reduces emissions is they basically dilute the cement with limestone, and in a way that doesn't that doesn't change strength very much. And by diluting it with limestone, you basically have less Portland cement per ton of cement, and therefore you have lower emissions. So for us, we're talking about making Portland cement. So you could also dilute our Portland cement with limestone, and it would have some benefits. Because it's carbon negative, it may actually be higher emissions. But that's a little bit different of a story. But if you like the properties of Portland limestone cement, type 1L cement, more than Portland cement, then you could certainly dilute our Portland cement with limestone and make Portland limestone cement. That would be no problem. Because again, it's the same material. So yeah.
Is it probably true, my understanding, that wherever the project is, that's typically people are sort of at the mercy of what's their local. I mean, we kind of joke with LEED, people always used to get the local regional credit with cement because that's what there was. You're not ordering it from 1,000 miles away. So what I'm getting at is, you kind of gave some really good call to actions, which was great. I appreciate that. But, I'm putting my hat on as like the consultant or developer or architect who's specifying these products. And at the end of the day, I would encourage them to go to their supplier and encourage them to, get this. But it seems like really they're just at the mercy of whatever's closest to the project. Is that accurate?
Yeah. And so for us, I think it's, it's certainly calling up your concrete company, encouraging them to come to chat with us would be very helpful, right? Showing a demand signal is always a great thing to do. So if you consume a lot of concrete, definitely reach out to me and I'll tell you to do that. Or you purchase a lot of concrete, and do that. But right now, you can't buy our cement. We're too early. Unless you're building a dollhouse, we don't make an appropriate amount of cement. So, and yes, like the point is, we need to scale globally. So availability of rock, that was someone's question before. We have high availability of rock, so we have the ability to install this process and anywhere in the world. So it will take time, and these global transitions always take time, as we saw earlier in the presentation. But that's definitely a key part.
What about, I think about projects that recycle concrete. We do a lot of renovation projects where we administer green programs, and so they're always picking up points to recycle their concrete. What happens to something like this on the back end? Is that part of the negative carbon data you have?
We didn't use, so our LCA and the conventional LCA all stops at the plant gate. So certainly concrete recycling could be helpful, and we love concrete recycling, definitely do it. And there's also some emerging technologies, actually including ours, which could recycle cement from that concrete and turn it back into Portland cement. So there's really great, definitely recycle concrete. That's not involved in our LCA.
Okay, but to be sure, I guess the second part of my question is, it's not going to harm the recyclability of it.
No, it's the same, right? So yeah, it's just like steel is made by multiple processes, and you end up with the same material. This is just a new process to make the same material.
Yeah. So there's a pretty big question here. I don't know if you see it there, but a couple of questions. I hear your point about the fossil fuels being cheaper, and also you get fly ash out of the process as an SCM. The question I have is, other than greenhouse gases, there's still other chemicals released from burning coal, even with existing emissions capture technology. Is there a long-term plan to transition to cleaner burning fuels? And this almost sounds like more of a question to energy providers than you, but
yeah,
could you, do you want to take that a little bit there? So
yeah, I will agree with that. So yes, absolutely. So I would agree with that statement. Like we said, we believe that it needs to be a lower cost product in order to be globally adopted. Anywhere where there's clear market demand for a higher cost product, it is in our ethos to use the cleanest burning fuel possible, or electrification. But there has to be the demand for that, because if you make it, we could make a minus 500 kilogram CO2 plant that uses clean electricity, but if no one buys it, it doesn't have any impact. And a bank's not going to finance that plant if people aren't going to buy it at the higher price and everything like that. So yes, I would say that our plan is to use the cleanest energy source possible, and whatever is possible would be defined by market demand and economics. And I agree, coal is not great. So I would vote for regulations to, or as coal has other emissions problems, I would vote for regulations to limit those emissions and all these sorts of things. I would be very pro that.
So, I've seen this kind of around before, haven't seen it in a while. It came up here, and, you can address it. The sort of thought that comes up around that, these cement products, concrete products, have radon coming out of them still after they're produced. Is there, any proof to that, any thought to that, and how does what you're proposing change that?
Yeah, I don't know, to be honest with you. I have no idea. I would be certainly surprised if ours was any different than conventionally produced cement, because there's nothing else different about it. So I wouldn't want to make we just don't know enough to make a claim there. But we've never even looked for radon. But I know that, the calcium silicate rocks, they're commonly quarried for aggregate, right? So the major component of concrete. So there's no, that's actually mostly what's in foundations and walls is aggregate. So I wouldn't, I would be surprised if there's anything different about our cement and a conventional cement.
Right. I'm not sure what that question is. So, well, yeah, Cody, I don't know if you want to display again where people can go to contact you, learn more, if you want to put that up on your screen.
Yeah.
I forgot to put it in my slide here. And again, just remind us of that last minute call to action before we wrap up.
Yeah. So absolutely. And I see that last question from John Klein.
Yeah, if you want to take it, yeah, go ahead.
Yeah, I understand. I can take it. So John Klein is talking about, the rocks that we use, like basalts or calcium silicates. He says that the calcium oxide content is rarely above 25% unless it's limestone. What about all the other minerals? So it's a great question. So to try to translate that for everyone. So calcium oxide is the main ingredient in cement. Like maybe it's typically 65% of cement is calcium oxide. And in limestone, the other material is CO2. In our calcium silicate rocks, the other material is going to be typically silica, alumina. So that's silicon dioxide, aluminum, or dialuminum trioxide, and then iron oxides, either iron oxide or di-iron trioxide, to use sort of the most basic chemical term. So those are also ingredients in Portland cement, which is the convenient thing. So Portland cement is a mixture of calcium oxide, aluminum oxide, iron oxide, and silicon oxides. So those other elements help us make the Portland cement. And then those elements are also ingredients in Class F fly ash. So Class F fly ash is also silicon oxide, iron oxide, and aluminum oxide. So when we use these calcium silicates, we have to, per ton of Portland cement, we have to mine some more rock typically, but per ton cement, we mine about the same rock because we also make the supplementary cementitious material, which is a component of the cement. Whereas a conventional company would mine the limestone to get the calcium oxide, and they would need to mine another rock to get the aluminum and the silicon and the iron, and then they would need to buy a third thing, which is the fly ash, in order to get that source of silicon, aluminum, and iron. So, John, please let me know if you want any further clarification on that.
Great. Thanks for elaborating on that one. So yeah, again, Cody, we're at the end of our time here. I don't really see any other questions, but I really appreciate you coming out and talking with us on this important matter. And we hope to see, you all succeed so we can have our team start specifying negative carbon cement. So just again, real quick, where can people go to contact you, and what specifically are you looking for?
Yeah, so email is info@brimstone.energy. And the three things that we're most looking for is if you are a chemical engineer and are curious about working at Brimstone, or if you know a really good chemical engineer. If you are connected to the purchasing of greater than 10,000 tons of cement or greater than 40,000 yards of concrete per year, then we want to hear from you. And if you are a policymaker, be that public or private policies, so that could be, low carbon cement laws, or it could be LEED standards or ASTM standards or ACI standards, we want to hear from you too. So please email us at info@brimstone.energy.
All right. Well, thank you so much, Cody. Take care. Have a great rest of your week. Stay well, everyone. Goodbye.
Yeah, thanks so much for the opportunity, Brett.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.